Okay, so let's take a look. All right, if we look at our carbon skeleton, remember that's the one that's hard to change. I have 5 carbons over here. Right, but over here I have 6 carbons. So I'm losing a carbon, right? And we really only know one good way to do that right now, which is oxidative cleavage, right, of an alkene. So that means that at some point I want to potentially have an alkene here, right? And if we think about an alkane, what type of reaction can an alkane do? Well, an alkane can really only do one thing, which is do an alkyl halide reaction, right? So a radical alkyl halide reaction, and then I should be able to get from there to there, right? So the functional group transformation is forming the carbonyl. I know I'm losing 1 carbon, so therefore I need to do the oxidative cleavage here, right? That's what ozonolysis. I need to do an elimination here. And what type of an elimination? Well, this is not a Zaitsev, this is going to be a Hofmann elimination. And then here I need to do a halogenation, right? And that's going to be a radical. So I need to do a radical. That's horrible writing even for an iPad and me. Radical halogenation. Okay. All right. So if you had gotten to this point within a minute, hey, you're doing really great. So let's look and see what this looks like going forward. So I'm going to do a halogenation and I'm going to pick the bromide. Why the bromide? Because it's much more reactive, right? The bromide is going to give me that tertiary bromide 1,600 times more than it would give me the primary, and several orders more than the secondary. And then I need to do an elimination, and I want a Hofmann, which means I need a big sterically hindered base, so I can use the T-butoxide. That's going to give me the double bond where I need it, and then ozonolysis, which is ozone, right, followed by some type of reductant, either dimethyl sulfide, or we could use sodium hydrosulfide or sodium sulfite, and that will give us the carbonyl, right? And then the other part of that would be CO2. Okay, questions about this one? These reactions, as somebody pointed out last time, is really good review for all of your reactions. And so, I would start doing one of these a day. There's some in the book. You could have your friends make you one. You could share them, do rotation, but not hard to make up. Make up 5 on Monday, and then try and remember what you had done later in the week. But this is a good way to review your reactions and recall. Again, when we learn these things, you can say memorize, but what you're trying to do is you're trying to recall, right? And the more you recall these things, the more the brain will make the synapses to actually make this part of your knowledge. Okay, so moving into chapter 12, we have alcohols and phenols. Let me switch back to black. That would make a good album. So if we have, ethanol, we're familiar with that one. It is a neurotoxin, widely consumed by humans, but it is toxic. Here, cyclohexane. Right. Phenol. Go ahead and introduce the phenol right now. Phenol is an aromatic group with an OH attached to it. So this is my phenol. So we'll see in a minute why the phenols are listed a little bit different. and they are listed a little bit different because their pKa value is distinctly different. Nomenclature. The big thing here, right, is that we're changing our suffix. So therefore, whenever we look at this, we're going to be naming these as alcohols. Oops, left my pen in the place a little too long. Right, so if we look at this, I'm going to number my carbons. So I have 1, 2, 3, 4, 5, 6. So my parent name is going to be hexane. I am going to add the A for hexane, and then I'm going to put all, OL, right? And then for this one, this would be 3-hexanol. If it's really complex, right, I can put the 3 in front of the all. So that's, but again, you see this more when a molecule is really, really complex, would have lots of side groups. In this case, 3-hexanol would be the name. Now notice a couple of things. One, I'm still adding the AN. That lets me know that the base structure is an alkane, right? But the priority, the name is an alcohol, right? So that gets priority. As priority, that means that I want my alcohol to have my lowest number, right? So if I have choices, I want my alcohol to have the lowest number. So if we look at something like this, right, now we've got an ene, we name our longest chain, right? 1, 2, 3, 4, right? This is going to be bute. Well, I need to put a U in my bute. Butene all, right? Now on this one, what I do want to do is put in, I can put in the 1, right? And then the ene would become 3. Why? Because I'm naming it as the all. Now, you'll see this one written as 3-butene all. Why would that be acceptable? And this is an acceptable IUPAC name. Well, because as the all, right, that has priority. And that could be 1, right? Now it could also be 2. And so the 1, this is your best name. Sometimes you'll see this. If you ever saw this in an old bottle, assume that that's 1, okay? It's always on, it's assumed to be 1 if it's not numbered. A good example of when it's always 1 is when we have cyclics. So let's say that we had this cyclic here, right? Then this one is going to be 3-chloro cyclohex. Again, there's no double bonds, so I have hexanol, and here the all is always 1, right? And notice here, to keep our number straight, we do drop the number. We do drop the 1 next to the all, right? So this is our best name. If you see this on an old bottle, you have to assume that's 1. In this case, in cyclics, the all is always 1. Like when we had cyclohexene, right? The ene was always 1, 2. Because I'm naming it as an ene, it always gets priority. So before it gets 1, 2. Okay. Let's try a couple. Let's take a little while to do these two. Did I just draw exactly the same molecule? I did. Let's do something a little bit more entertaining then. right, now if we look at this one, this is going to be pentan, right? We have the all is on a 2. And then we have the bromo, and the bromo is going to be on the 4, right? And we give the 2 to the all because that's what we're naming it as, the alcohol. On this one, we've got cyclohexene all, right? Make that a little better. Now I don't need to put the 1 for the all, but I do need to put the number for the ene, and the lowest possible would be 2, so 2, 3, but I only have to put the first number, so 2 cyclohexene all, the 1, the all is assumed to be 1, and then in this case, right, this is a good chance for you to review, right? We have 1, the H is 4, this with the double bond would be 2, this would be 3, so 1, 2, 3, that is going in the counterclockwise direction with my lowest priority back, so that's S. So this would be S2-cyclohexanol. So as we build up, right, it's always good to try some problems that have you flash back a little bit. There are some common names in alcohols that you do need to be aware of. You're probably pretty aware of these already. Okay. So we have isopropanol, or isopropyl alcohol. The IUPAC name on this one is actually 2-propanol, right? Here we have tert-butyl alcohol, or tert-butanol, right? And the IUPAC name on this one is 1,1-dimethyl ethanol, right? And sometimes you'll see the 1 all here. Here it has to be 1. In ethanol, it's always going to be 1. There's no choice. Okay, so you can see why we use tert-butyl instead of 1,1-dimethyl ethanol. And then this is our phenol, right? And of course, that's got it's a whole subclass of alcohols by themselves. Okay. And again, shouldn't be hard to know these. Phenol is probably the only one you haven't ran into in your normal life. Isopropyl alcohol is in rubbing alcohol. That's rubbing alcohol. Tert-butyl alcohol, we've been using that one in class for a while. It is important. Let's go talk about denatured alcohol. So ethanol is is taxed, right? So industrial ethanol is not taxed, or at least is not a taxed by alcohol, beverage, and firearms, right? Is not taxed beyond what normal merchandise is taxed. So this is called denatured alcohol, and it contains a trace, usually a trace of methanol. Now, ethanol in general at high concentrations will kill you, right? It is a toxin, but methanol right, is more toxic, and it can kill you. The most common effect of drinking denatured alcohol in large quantities is blindness, right? And then death. So they add the trace of methanol in there to make denatured alcohol. So if you ever see denatured alcohol, that is not consumable. And because it's not consumable, right, it's not taxed at the same level, right? There is a way to remove the ethanol, and there was actually a whole scheme of shipping what was referred to as denatured alcohol to the US, and then trying to remove the methanol. Turns out that's really tricky, and you can make mistakes on removing the methanol. It's not easy. So then they switched to sending what they called windshield washer fluid, which was ethanol with blue dye, and it turns out they were able to remove the blue dye much easier. It was a horrible scheme because the blue dye wasn't good for you either, but at least wouldn't make you go blind. But anyway, wanted to refer to denatured alcohol in case anybody runs across a big industrial 55-gallon drum of ethanol. Don't drink it. Okay. So let's look at acidity. So in general, alcohols usually have a pKa between 15 and 18, between 15 and 18, right? And so therefore, we'll look at how those change, but that's the range. And remember, water was 15.7, right? So in that range of water. So when we look at the main reaction of an alcohol, the main reaction is its acidity, is that removal of a proton. And so, when we think about that, we could look at, pKa here of 16 plus sodium hydroxide, right? And what we end up with is an equilibrium process, right? Because we have a pKa here of 15.7. So we have an equilibrium process, and this is going to be important not only in this chapter, but it's also going to be important when you get to carboxylic acid derivatives, which is very biological. So understanding the difference between quantitative and equilibrium-based deprotonations, and think about anytime you have like sodium hydroxide, water, and alcohols, this is going to be an equilibrium process. And there's going to be times where the equilibrium deprotonation is desirable. You can also have what we refer to as quantitative. Now, quantitative is an interesting term used by organic. My chemists in general don't like to be very exact with their numbers. And so quantitative is a way of saying all without saying all or saying 100%, right? So quantitative means whenever we're talking about a quantitative deprotonation or a quantitative process, that means that within the measurability of our experiment or our instruments, it is quantitative. I mean, it has gone to 100%, but we know nothing probably is 100%, and so quantitative is that term. And so if we think about alcohol deprotonations, if I add sodium hydride, right, what I'm going to end up with is a quantitative amount of the deprotonated species. So again, we don't like to say 100%, but you can say that this is going to happen. And because this is a gas, right, the hydrogen, this is not going to reverse, right? So this reaction is going to go forward, no reverse, right? The difference between the pKa's, right, the pKa difference between the hydrogen and the alcohol is very distinct, right? We're talking pKa value around 60 versus pKa around 16, and then we're losing the hydrogen, right? So this is going to go quantitative. If we look at this reaction mechanism, it's pretty straightforward. You know, the hydride is my negative here. It's going to pull off that proton. When it pulls off that proton, right, it forms hydrogen. And so sodium hydride, if I want to make sure that I've created all of the base and I do not have an equilibrium species, sodium hydride is a good way to do that. So this is a quantitative deprotonation reagent. Another one, which is a little bit trickier to work with, is sodium hydride, but work industrially is actually the way you'll see this done most, is just to add sodium. It's a little tricky in the lab, and it's kind of thing that we probably wouldn't want a sophomore lab to do, is because sodium in water, right, can catch on fire. And it turns out that if you're not careful here, you can also catch on fire because you are giving away, or you are putting off the hydrogen gas. Now, in the first one, the sodium hydride, that's a low enough energy, but with sodium, you are doing a 1 electron reduction, right? And the sodium is going from this to this, right? So it's losing that electron, giving it to the hydrogen. The hydrogen is reacting with another hydrogen, and so we're getting this species. So the two quantitative reagents we have are the sodium hydride and then just straight sodium. And as we go through, you'll see places where we want to use either an equilibrium process, just sodium hydroxide works fine, or a quantitative process where we want to make sure that we end up with all of the deprotonation product, usually for a second step, right? We want it all deprotonated, so then we can go and do something. And sodium hydride and sodium are the main reagents for that. So if we look at pKa values, the things we want to look for different alcohols, again, they're all in this tight little range, but sometimes it's going to be important to know which one's more acidic or basic than the other. So if we look at, our phenol and the non-hybridized version of that, so here we have pKa equals 18. Here we have pKa equals 10, right? Because of the resonance here of the conjugate base, right? That's going to stabilize this quite a bit. So one of the things to watch for is resonance stabilization, right? So resonance stabilization will make it more acidic because the conjugate base is more stable. So one thing we want to watch for is resonance. That'll tell us if something's going forward or backwards, right? So whether something is more or less stable than the other alcohol. Induction. And really what we're doing is rehashing the chapter on acid base and figuring out which is more acidic and which one is less. So if we take ethanol versus trichloroethanol, or 2-trichloroethanol. So here we have a pKa of about 16. Here we have a pKa of 12.2, right? So here, when we look at the conjugate base, we've got our chlorides here. All of our chlorides are causing a dipole moment, pulling electron density towards themselves because they're more electronegative, which will then cause a pulling away from the chlorine through through the bonds, right? So not a direct movement of electrons, but electron density. Right, so the inductive effect. And I'm doing a little bit of this to review some older concepts. The third one is solution of solvent effects. And now the solvent effects aren't like the ones we saw with SN1 and SN2 and the stabilization of the carbocation. Here it's actually the solvation effects of just it as its own solvent, right? So if we look at this one, right, this is our kind of standard pKa 16, but here we see we have a pKa of about 18, but electronically there is no resonance, right? Electronically, there's no big inductive effects, right? We're not going to see that tertiary carbon here really is not going to change the electron density unless that was a carbocation, and it's not, right? So what we're looking at is what is happening, and what's happening is as we look at the conjugate base, right, the amount of solvent that we could potentially, you know, interact this with, and the solvent would be other p-butyl groups, is going to be a lot less than if we look at this species where we see, you know, a much bigger window for the solvent. So big bulky groups decrease the solvation stabilization of that counterion, and that's going to make it less stable, right? So a larger pKa, less acidic, right? So smaller alcohols that can allow more solvation of the conjugate base is going to have lower pKa's, where big bulky alcohols where you'd have less solvation. And that's the reason we have the difference here. We're two electronically similar groups, but because of the sterics, we see a pretty significant, I mean, 16 to 18 is pretty significant. It's not quite as much as the inductive effect, but it still would be enough to shift a reaction one way or the other. Okay. Right. Any questions about this? Okay. All right. All right. So preparation of alcohols. And this is a good time to kind of point out the kind of the framework of the rest of the chapters, and this is kind of standard across all textbooks, is that by this point, you've got some preparations that you've already seen, right? So therefore, some of the reactions you're going to see in each of these chapters are actually review reactions. And so if we think about preparation of alcohols, we already know some of those. And the first set is substitution, right? If I take a halide and react that with sodium hydroxide, I can substitute and get the alcohol, right? So this is just an SN2 process, right? So I already know that. This is review. I'll try and note when something is review versus something being new. I tend to focus on new. So if I forget to put the, okay, so if you look at, let's go back to the solvation, got a question about solvation. If we look at these big bulky groups here, right, when this is insolvent, right, these groups are going to change the ability of something to solvate with that. So if we look at the minus here and the H here, because this is big and bulky, it's actually just not allowing enough space. So it's just too crowded. So I could think about here kind of, I got maybe a semicircle of space where I could bring in 3 or 4 solvent molecules to stabilize that negative. But over here, because really it's just the methyl that is causing a proximity problem, that, you know, now I'm getting about 270 degrees of solvent. So I could bring in maybe 5 or 6 or solvents, right? Here we might be talking about 3 or 4. And so we're increasing the amount of solvents that I could get, and probably should show that by putting in more solvents. And this is a guess. We'd actually have to do modeling, which they have done on this, and probably could find an article with that. But here, right, we're just going to have to, maybe we get 3 to stabilize that anion, where here we're going to get, many more. Okay, so preparation of alcohols. So we've seen this one. The other one we've seen is the SN2. Here, all we need is a weak base, so we can just use water and get solvolysis, right, to get us the alcohol in an SN1 process. So we can form alcohols using SN2 and SN1 processes. Okay. We also have addition reactions. So if we start with an alkene, I could end up with an alcohol using, water and acid. I could end up with an alcohol by using oxymercuration, demercuration. Followed by, mercury acetate, followed in water, followed by sodium hydroxide. And then I could end up with the least substituted by adding the sodium borohydride plus the basic hydrogen peroxide, right? And this is all review. We've seen these before, right? This was review. Okay. Now under the new, right, now we're going to expand. Okay, so we're going to prepare some through reduction. First thing to think about is oxidative states. Okay, this is a little bit different than your oxidative states that you might have learned in general chemistry. In organic, again, remember oxidative states often deal with fully ionic, and here we're dealing with a lot of covalent. So for this, the way to think about it is to consider whether we have a less electronegative atom or a more electronegative atom. So if we think about it, we treat them all as covalent, right, we are going to end up with radicals. But here, if we treat them as ionic, we can see that the oxygen negative here, well, the oxygen is more electronegative, so it would have a negative, but the hydrogens are less electronegative than carbon, so they would have positives, which gives us the number of electrons we'd have in an oxygen. So it's looking at these and assuming what we have attached to it. So if we think about, if we had a carbon with 4 oxygens attached, all 4 of those oxygens would be more electronegative. So therefore they would take all the electrons and the carbon would be left with no electrons, which would mean a +4. right? So the idea behind this is looking at the electronegativity of what we're attaching. And so if we look at some standard species here, methanol, right, any of our ethanes without anything attached, that's going to be a -4 because the carbon is more electronegative than the hydrogen. Methanol here is a -2. We can see that from this example up here, right? Because plus and 3 negatives gives you a -2. Once we get to formaldehyde, right, we've got 2 less electronegative atoms, but now we've got 2 bonds to oxygen. So therefore we're going to have a +2 on the carbon and a -2 on the carbon. So +2 because the oxygen takes the electrons, -2 because the hydrogens give up their electrons. So that gets to 0. Once we've added 3 oxygens, we get to +2. And then when we have carbon dioxide, right, we get to +4. Okay. There are some practice problems on here, and it is good for you to look at these and understand. It's really has to do with doing this right here, right? So let's take an example. What would be the carbon oxidation state here? Well, we know that the chlorine is more electronegative, right? So if we draw it out in that kind of form, the chlorine is going to get the electrons here and be negative. So that's going to have to be positive. The chlorine here is going to get the electrons, so that's going to be positive. But then when we look at the hydrogen, right, it becomes positive since it's less electronegative than the carbon, and the other hydrogen also, right? So we have 2 pluses and 2 minuses, right? And so this would have a state of 0. Reactively, what this is important is to know if I went from methanol to formaldehyde, that's an oxidation, right? Oxidation. And going the other way, right, is reduction. So what we're looking at here is, can we form alcohols by reducing carbonyl species and I shouldn't, can we can take out carbonyl species and reduce those to alcohols. Okay. So the third area of preparation of alcohols, and this is a new area, is going to be looking at the reducing agents that we can use for this. Okay, and that's probably all we're going to have time for today. But if we look, the first one is hydrogen, is familiar, right? Hydrogen, platinum, palladium, or nickel, right? So we just need a good reducing agent, right? So we can do that one. Pretty straightforward. The other one is something we've seen in other cases, but sodium borohydride, right, and methanol. Hydrogen and palladium, platinum, or nickel just need one of those metals, not all three. We see that really works the same way we would expect. The mechanism very similar to reduction of a pi bond in an alkene. Here, what we have is the BH is what we refer to as a hydride donor. And we've seen it in the second step of oxymercuration, demercuration. In this case, the mechanism is well known. The sodium borohydride, the hydride attacks the carbonyl carbon, right, and kicks off, breaks that pi bond. that results in the oxygen negative, right? We've added a hydrogen. And then the methanol becomes our proton source, or any solvent. Most often they're going to be some type of alcohol. That becomes a proton source. And again, here, because it's our solvent, even if we have an equilibrium process, we can drive that equilibrium process forward to protonate our desired alcohol. Now, because of this first addition right here, this is going to be racemic. So if we look at, sodium borohydride reduction, and here I'm going to change up the solvent just so you don't get stuck, ethanol, right? I'm going to end up with either addition to the front or to the back, right, in a equal amount. So that's going to be racemic. And that's because we start with a planar starting material. Okay, since the carbonyl is planar. Carbonyl is another word for, it's not another word for ketone, it's another word for this species, right? Where you have R and R. So a aldehyde has a carbonyl, a ketone has a carbonyl, carboxylic acid groups have a carbonyl, right? So the carbonyl is the C double bond O. And so although it's shown ketones here, this also works for aldehydes. The third reagent class you have here, and let's do this one before we stop today, is a different hydride donor. It's lithium aluminum hydride and water. Notice 1 and 2. This is a two-step process. The result is the same, but lithium aluminum hydride is more reactive than sodium borohydride. And so this one can be in protic solvents. This one needs to be in non-protic solvents. What would happen is we put lithium aluminum hydride in water, it would give off hydrogen, create lithium hydroxide, and potentially catch on fire because it gets so hot, and we wouldn't get the reaction. So this one needs to be in the non-protic solvents. So if we look at the way this works, it works the same way we saw the other one. It is a hydride donor, it's just more reactive. We have the hydride attacking the carbonyl position, carbon of the carbonyl position. We end up with this, and then step 2, then we add our water to get us our final alcohol. So we have to add the water to reprotonate to form the alcohol. Okay, and with that, we've run out of time. We'll continue in alcohols on Friday. We'll get a quiz posted. Friday, you'll have several days to work on that one. Again, it's for your practice.